Coming back to the teleportation concept. What exactly do you mean by teleportation again? Can anyone say that? Okay. So simply to put, the real information will go from one place to another without actually passing. So when I say without actually passing, it doesn't mean that there won't be any sort of communication. That's the first thing which you need to identify. So when I say that the information is not being passed or the information is not being communicated, it does not mean that there won't be any sort of communication. Okay? So it does not mean that there won't be any sort of communication. Definitely there will be a communication, but the communication of the actual information will not be there. Understood the point? So the point goes like this, that is, communication will be there. Communication will be there. That's the first thing. Okay, in teleportation, when I say that the information will not pass, it does not mean that there won't be any sort of communication. No, it is not the meaning. The meaning is that communication will be there, but the communication information will not be communicated. But actual communication line and communication stuff will be there, will exist. Those guys will exist. That's the first thing which you need to identify when you are actually talking about teleportation. Okay? So normally teleportation is the meaning of this particular thing. That is the communication of the information will not be there. Don't keep in your mind that communication will not be there. No, communication will be there. But actual information will not be communicated. Got it? So that's the first thing to identify. Now let's go to the step-by-step procedure of this particular. Okay? First, what will are the sender and receiver transition period. So this transition guy has the information. That's the first. This transition guy has information. And A is the sender. And B is the receiver. Okay? Now what happens is that in this case, this A guy has these two qubits. So let me name it as Q0, Q1 and Q. A has, that is my sender has these two qubits. Okay? And my receiver has only one qubit consists of the information which he wants to send. That is known as the transition qubit. And second qubit which is having is the helper qubit or the connector qubit. Okay? So the information will, and the other qubit which Alice has is used for communication or is used for all the type of service we are doing. Now, first thing what happens is that this can be any string. Okay, that's also one of the things. Let us consider that Q0 can be any information. Once you know, super text coding, we had that rule, right? It's 00 identity, 01 X, 10 C, and we had a rule. But here we don't require any type of rules. Okay, Q0 can be any sort of information. But it can be any. I will entangle by Q1 as well as this particular Q2. Actual Q2, not the information. And then what I will be doing is that I will do a bell measurement. I will, in a sense, I am the sender. So I will do a bell measurement on my transition qubit as well as the helper qubit. I myself will conduct a bell measurement there. Because what I have two qubits color. So for entanglement, it's not a requirement that I need to have two qubits. That's the first thing to identify. In yesterday's session also we might be confused with this, but a point goes like this. For example, I am having a qubit and you are having a qubit. I can entangle two qubits, not a problem. It's not like I should be having two qubits. In order to entangle share, should be right entangle share. Not a problem. Okay? So in that case there won't be any problem. So that's how qubits with myself. For example, ఇక్కడ Alice దగ్గర ఒక qubit ఉంది, Bob దగ్గర ఒక qubit ఉంది. Alice cannot perform, it cannot do that. Has Q1 with him or with her, sorry. And Bob has Q2 with him. So when I am not having those, if I want to perform the bell measurement, our two qubits not okay, entanglement ki adi avasaram ledhu. Entanglement ఏమవుతుంది అది వేరే దగ్గర ఉన్నా కూడా entangle చేసేయచ్చు, ప్రాబ్లం ఏమీ లేదు. Got it? But when I want to actually perform the measurement, I need to have all the qubits with myself. Then only I can perform the measurement. Now, after entangling, the next is which she is having. So what is the bell measurement? Hannah. Got it? Alice will perform this operation. ఎందుకంటే Alice దగ్గర రెండు qubits ఉన్నాయి కదా, transition ఉంది Q0, Q0 ఉంది Q1. So Alice will perform bell measurement. After this, what it will do? It will measure the qubits. No. This is the calculator because Alice will do this with respect to Q0 or Q. Q0 on Q.
But we thought Q1 on Q0.
Q0 on Q. Okay, this is known as bell measurement. It is I apply C0 gate, I apply Hadamard gate, and then I measure the two qubits. So this complete thing is known as my bell measurement. Okay, so that is I apply the Hadamard operation. Sorry, I apply the C0 operation, and then I apply the Hadamard operation, and then I simply measure the two qubits. Okay, this completes my bell measurement. So my Alice will perform the bell measurement on the qubits which she is having. Okay, so now I have two classical bits 0 and 1, and then this is not the information. Okay, that is not the information. 0 the growth, 0 message or 0 message card. That is the name of the classical bit. And also here I name petkoni A B I petkoni not a problem. That's the name of the classical bits. Okay. So right now, after measuring the two qubits, what will be my output be? My output will be two classical bits. Yes or no? That's what I thought about the quantum state. That quantum state will be decomposed into a classical particle, and that classical particle's information will be stored in a classical bit. That's the primary concept behind it, right? So it works in that simple manner. Got it? Yeah. So these two measurements will be stored in classical bit 0 and classical bit 1. Okay. So now after performing the bell measurement, the Q0's value is stored in C0 and Q1's value is stored in C1. Is the qubits holding my actual quantum state? Yes, are not holding my quantum state. These two qubits are not are not holding by quantum state, but they are simply being the measured ones of this particular bell measurement which is being done by hands. But they are not actually storing, nor they are actually representing a quantum information. The actual quantum information in 2 bits and represent cheyalలేదు. They are just being that. Got it? Now what happens is that these 2 classical bits are there. They will be sent to Bob through a classical manner. Like optical fiber gaani, waves gaani, internet gaani, ఏదో format లో these 2 classical bits of information. Classical bits పంపడం ఈజీయే కదా, సేమ్ ఎవ్రీడే అలా పంపుతాం, క్యాష్ వాట్సాప్ మెసేజ్ అలా పంపుతాం హాయ్ అని చెప్పి. అట్లనే ఈ 2 bits of information ఉంది చూసారా, these 2 bits of information will be sent to Bob, okay, through a classical channel. Why? Because this itself is a classical information. These 2 classical bits itself is a classical information. So this classical information will be sent to Bob through a classical channel. Got it? So that's one. So this is the complete circuit with respect to the sender's point. Sender's point of view, this is the complete circuit. Okay? Now the second is qubits are sent to Bob. These 2 qubits are sent to Bob through a classical manner. Okay, and now Bob has 2 qubits. I mean 2 bits with him. 2 bits of information. 0001, 101. In 4 cases, no, ఏదో ఒకటి ఉంటుంది వాళ్ళ దగ్గర కదా. Because 2 bits of information అంటే we will have 4 possible outputs. Because 1 bit of information can hold 1 value కాబట్టి the 4 possible outputs of this 0001 are, I mean classical bit 0 and classical bit 1 are either 00 or 01 or 10 or 11. So this is the possible output. Okay, so our 2 bits of information can be edited in these 4 options, yes or no. These 2 bits of information can be edited out of these 4 options. Why? Because 2 bits like up to 11 options. If I am having 3 bits, how many options will I have? 8 outputs. Our 8 outputs will any one of the guidance in my answer. Got it? Now, in 2 ways, I have 4 outputs. Now, based on the bits of information which Bob is receiving, he will perform some operations on it. Okay? Yeah, just keep this thing outside, but I will tell one another stuff as well. Theoretically, if Bob receives 00, he will perform nothing. If he receives 01, he will perform X gate. 10 C gate and 11 Y gate. Okay, this is the rule for that. If my Bob is receiving these between one thing options based on the stuff which he is getting, he will perform any one of the gate. Like ఒకవేళ అతనికి 10 వస్తుంది అనుకోండి, C గేట్ అప్లై చేస్తాం. అదే 00 వస్తే A అప్లై చేయడు. అదే 01 వచ్చింది అనుకో, X గేట్ అప్లై చేస్తాం. 11 వస్తే Y గేట్ అప్లై చేస్తాం.
He will apply that on Q2.
Yeah, Q2. He will apply that on the Q2. So like that, he will simply apply the gates. Okay, so in that way, he can, once he apply the gates, and then once he measures his own qubit, the final output will be the original first state of Q1. Okay, so what he will be doing based on the 2 bits of information which he is getting, he will apply any one of the gate or his own qubit, that is Q2. Okay, after applying any one of the gate on Q2, then what he will do? He will measure the Q2. He will measure Q2. He will apply some of the gates based on a particular qubit, based on particular bits he is getting, and after getting the bits of information, he will apply the particular gate on his own qubit, and after applying that particular gate on his own qubit, he will simply measure that particular qubit. Okay, and after measuring that particular qubit, this output is there. This output will be the state or will be the measured output of qubit. What the state of my first qubit is. Understood? So this is how my actual teleportation works. So why it is called as teleportation but not communication? Very simple. This Q0 information is not being communicated anywhere inside this computer protocol. If you read this protocol again, since the beginning what I told at each and every step, each particular piece of information which is there, the Q0's actual quantum information, that Q0's quantum state is not being communicated. Q0 in message the state classical that communicate type the actual quantum state of the Q0 is not being communicated. So that's where the teleportation term comes into play. So that's why I told in the beginning of the session itself, teleportation is not equal to no communication, but teleportation is equal to no communication of information.
When you get the theory of like an equivalency?
We will directly show that in the output itself. That's what I will show that.
Theoretical equivalency.
Theoretical equivalency will be by using the entire matrices of operational stuff like that.
So that we can do later on.
Yes, that we can do later as well actually. And how we can actually find the actual output and how we can actually say that they are equal and simply to put. Totally in that entire system, how many qubits we are having? We are having 3 qubits in our entire system, right? But on measurement, these 3 qubits will, because of this probabilistic nature, these 3 qubits will give 8 outcomes, right? So this is the thing which I will have. But when we perform this teleportation theory, what happens is that we won't be getting 8 outcomes. We will be only getting the 4 outcomes in which this equivalency is satisfied. So in that we can find that okay, so thereafter when you measure, you will be getting the 8 outcomes and each stage one output was there. But when this teleportation happens, then 8 outcomes will be limited to only 4 outcomes where this equivalency is, what is preserved or this equivalency occurs. So that's how we can do it.
Any specific resources are available just to learn about this?
Yeah. There are a lot of resources actually. Like you will be having, and recently there are very lot of resources on this purpose.
Like just to learn about this.
Yeah. Yes, sure. We will be having Geeks for Geeks also. You are having this actually. So there also you will be having it, or IBM official website where you have, and ION Fuse theory. So you are having a lot of guys. So there you can see this. Now, trying of the case. Here the problem comes when the output is not normal or when the output is not so specific. So why? Because in some cases, what happens is that some people don't want to send these bits of information as well. Or some people don't even know what these information might have as well. Okay, so in those cases, instead of giving this rule-like format, like here it's a rule-like format, right? If the bits are 0, 0, then you should apply IIT. If it is 0, 1, then you should apply XK. So it's like an event rule. But in some cases, what happens is that some people don't like to, or they are not willing to send these bits of information, or send these stuff of information, or they don't want to keep these particular rules, simply to put. So in those cases, what happens is that directly, in those cases, we can apply, or the bomb will apply a series of measurements or a series of gates, irrespective of what the classical bit information is. So one of the series of measurements are, so there are a lot of measurements, but the most prominent one is CX and CZ gate. So this is the most prominent. That is, what happens here is that instead of applying that particular gate thingy, or with respect to if then gate prakar, like ala kaakunda, the Q2 or the bomb, what he will be doing is simply, he will create a CX between himself and he will create a CZ between the transition Q. Okay? So, this is control and this is target. So what happens here, simply put, discussed here my entire measurement is done. So that is why all steps are done till here. So you can all steps motto IPD and okay, that entire measurement is done. Now what my Bob will do, he will simply apply at C0 gate here. Apply a C0 gate. That's it. So when
Question comes
it won't even happen. What happens is that this guy can perform this access directly. ఎందుకంటే ఆ quantum state అనేది నా classical state కి మారలేదు ఈ case. So when we are trying to use it, not even happen. So in this case, where the measurement doesn't even happen and Alice don't want to send any classical bits of information, everything will be the same quantum state or everything will be the same quantum system. So that's why what he will be doing the Bob will be simply creating a gauge with respect to these qubits then. So he don't need to have these qubits with himself in order to create this particular gauge because as he is not yet measuring them simply. So what he will be doing, he will be simply initializing these gates with respect to those qubits with mass. Obviously when during a teleportation, they have to communicate with you. What happens? Obviously yes, prior communication with that. I will be telling you already, bro, I want to teleport an information to you, but I don't want to send a classical bit of information. So you try to do that. Like that, I will be telling you before it. Why? Because we both are agreed parties at it. So that's how it is.
And then the other question, yesterday's class we had SDC where the encoding is fixed. That's what is your like 00, I400 and this is how. And here whatever we have just taken, they are also agreed between two parties before.
No, that's a rule actually.
This is also a rule.
This is so that's a rule. The encoding thingy which we have seen is a rule. So I cannot say that bro for one I will use X gate and then shuffle it. That's a rule like the max rule is. But this is an agreed party thing. So and yeah, this CX and CZ operation is there. This is also agreed upon the parties. So this is not a rule. This thing is not a rule. It is rule card. It is not a rule. So this is just one of the method in which I can actually add this. And Bob will receive those two bits of and then he simply measures the so as to get yeah, same thing. The output will be Q2 only. But in this case, what happens is that all the qubits will be measured at the same. So that is after applying the CX and CC operation, all three qubits will be measured at the same time. Like okay, so classically, so here you can see all the three qubits will be measured at the same time. So this is what will happen in teleportation in one another. Got it? So there will be technically two types of circuit diagrams which we can achieve by using teleportation. One, by performing the measurement before itself and by using a rule-based logic. And number two, by not performing the measurement before itself and using an agreed logic and performing the operation. So in this way, what happens is that once you perform this particular thing, this piece of information will be the initial information. Or that's about entire code, right? The initial state should be going to my queue. That's my main code here. Okay? So without actually transferring this piece of information, without actually transferring that piece of information, will not get this. When you have three bits of information, the possible outcomes are operation. Three bits of information. So therefore you will be having 8 possible outcomes. But when you actually measure the output of this circuit, you will only get 4 possible outputs rather than 8 possible outputs. Why you will get only be equal to initial? Why I am to final, the final Q in the stuff. So cloning. That validity is called as no cloning theorem. What exactly do we mean by no cloning theorem? Very simply to put, in the entire universe, no two qubits can have same state of information. For example, Q0 होते, Q1 होते and Q2 होता. No two qubits will have same piece of information or will have same state of information. Again, the entire universe. Okay, it's not only with respect to by circuit or not only with respect to that particular thing, other cars. In the entire universe, those two qubits will have same state of information. Got it? So now in this case, what happens? In this no cloning theorem, right? Yes or no? Can you guys identify this particular thing? Okay, for action. So why? Because the probability of the deep inside amplitudes will be definitely different by even 1 point aspect. So that won't be a problem. Okay? So when రెండు zeros, like that's what I told during the beginning of the circuit, or destroyed in that particular process. Again, this Q0 information is destroyed. So in reality also it will happen in this format only. So how many of you are physics lovers typically to put? Okay, 1, 2, 3. More boys. Nice. So what happens is that after Big Bang occurred, what happened in the first 3 minutes of the Big Bang? So then we are having the reverse things and all this is coming together. This guy worked there as well. This no-cloning theorem came there. Because in the beginning of the time, what happens is that everything were the deal goes like this. So everything were in quantum scale like that. So as they all are in quantum scale, those two qubits have the same piece of information. And the qubits which are very much close to each other try sharing the same state or try sharing the same piece of information. And because of this no-cloning theorem, what happens is that the qubits which are sharing or which share the same piece of information got destroyed. Simply put. So that's how most of the matter got destroyed there. And the second type of destruction occurred in the anti kind of. Like for everything we have the anti stuff and they got negative. And the remaining pieces are the things which we are seeing right. So this no-cloning theorem is there since that time. That is since the Big Bang time. So that's the thing which I wanted to say.
After that value was destroyed, we initialize it to 0 or 1?
It will be going back to 0. So when I say the value gets destroyed, what happens is that really in physical, what happens is that it will not be of any use after that point of. So
another we are giving the initial value of any qubit is 0.
So we will be having these graphs like this and use so for that as well you can use the same. So it goes in that way actually. Now coming back to this particular stuff, what is that? When I say the qubit is destroyed, there are two main things on the stuff which I am actually trying to take. First thing is, if I don't want to use, if I don't want to waste my resources, when I talk about actual quantum computers, like IBM, Harvard or something, then what will happen? I will simply discard this qubit. Okay, I will simply throw them off. I don't care. I will simply throw them off. I will discard. Else, the second case. The second case is I will take them to an initial state. I will take them back to the beginning because initial state. Okay, Q naught final state is equal to Q naught initial state. That's primary goal. Got it? So this is how we will perform the no closing. This is how we perform the quantum hypothesis. We will be having two type of circuits. Try to draw the full circuit. I'll just give it off. So consider I made my Q dot be in one state rather than zero state. I can make Q application problem at A. So, but for this case, I will think that my
సరే చెప్పండి పాస్వర్డ్ చేంజ్ చేస్తాను
ఇప్పుడు
నిమిషం ముందు చెప్పేసాను
హలో సెట్టింగ్ చేసే ఒక 5 మినిట్స్ అలా అవుతుంది మీకు ఏమైనా సరే క్వశ్చన్స్ ఏమైనా ఉంటే సార్ అడగచ్చు